Hello and welcome to the STEMCstudio channel and another video in the series Geometric Algebra First Course. In this video we are going to start a mini-series of about 4 or 5 videos in which we apply our geometric number to the problem of doing a physics simulation in 2 dimensions. Now, because this is a beginning series, I am actually going to build the whole thing from scratch in this particular video, but we will build upon it for the next 5 videos. The one thing I will reuse is our geometric number that we've built so far. But as far as JSXgraph is concerned and our visualization, I'm going to build all of that from scratch. Okay, let's get started. Okay, so the goal of the video today is to essentially just build the rigid body that we're going to have as our sort of modeling object and the visualization of that rigid body. In the next video after that, we will connect the position of the body to its velocity, and we'll connect its attitude to its rotational velocity, its angular velocity. Okay, so that's the goal for this video. Let's get started. So what I'm going to do is start completely from scratch with a minimal application, and I'm going to call it, I'm going to call this thing Flatland, because I actually have in mind to kind of create a little square, and this little square is going to move around 2 dimensions. So that reminds me of Edwin Abbott's little satirical novel, which is called Flatland. So let's begin. What we want to do is, we know that we're going to use JSXgraph. So I'm going to find JSXgraph, select the latest version. And to run JSXgraph, what I need to do is I need to have a div that it can live in. So I'm going to create a div, ID equals, and this is going to be my diagram, say. Okay, and I won't do much more beyond that. Okay, now in here, we'll remove the print hello world. Thank you very much. And we need to look for JSXgraph.initBoard. Okay, this is our function that is going to create our board for us. If we hover over that, you see the element ID is required. That's going to be our diagram. So that's the div ID that we have. And for right now, yeah, let's put in a few attributes for the board. Okay, so we can put in axis. Yeah, let's have the axes. And I want to have a bounding box. So bounding box, and this goes from xy to xy, but xy is the top left-hand corner. So x is, say, -5, y, and then +5, -5. That should do it. Okay. Code there. This is going to create our board. Let's just run it. And looking good so far. We got some navigation at the top, but we know the problem here is that we need to have a little bit of style in order to set the size. So we're going to set the style equals, and it's going to be a width of, say, 500 pixels and a semicolon, and then a height of 500 pixels. And there we go. Okay, let's hide our documentation. We don't really need that. So there's our board. I'm not going to do much more beyond that, actually, for right now. Well, maybe I'll just do a little bit more. So initBoard returns a board. So I'll say thank you very much. Got the board. And just to, I was expecting to get an error there saying that our variable is no longer used, is not used. Just to use it, I'm just going to say board.update for the time being. Okay, nothing much going on there. And if we want to prove this works, then let's just do board.create, and we're going to create, hit Control Spacebar, going to create a point, and let's create the point at the point 1, 2. The reference error point is not defined. Okay, I need to have that in single quotes. Not quite sure why I didn't pick it up, but we won't worry. We'll just speed ahead. Okay, So great, we've got our point. Now the next thing we want to do is we want to bring in our geometric number from our other project. So I'm going to come out to our home page. This is the project that I'm going to use. And if you haven't built the geometric number yourself yet, I hope you do, because that's an enormous part of the learning. But if you haven't done it, you can still use this gist ID here, and you can follow along with this project and then kind of come back later and maybe put your own geometric number in there. Okay, so I'm copying that gist ID because I know I'm going to need it to do a reference in my Flatland project. So I come into my Flatland project, I unhide the configuration files because what I want to do is I want to modify my package.json file, and I want to add a property which is called references. Now references is a map, and the key to that map is a file name. And I should have pointed out that the file that we're going to bring in is called e2ga.ts. That's the file as it is called in the other project, and it will have the same name in this project. Okay, and then here we have a data structure repository. We have to specify what repository, if you like, or where this file is going to be found. And it's going to be found in the gist, whose ID is, and if I go Control V here, there's my gist ID. And with any luck, this will work. So what we need to do is go to our project menu, select Pull References, which we do. And as you can see, oh, it's not coming in. But the reason for that is because hide reference files says it's true. Okay, there is a setting for that in project settings. So I could make that false, or I could say uncheck that, and it vanishes. So now we can see re2ga.ts. So all is good. Let's just check. We can run the project. Yep, and we've got our geometric in our project. We are ready to go. So what we're going to do is we're going to create first what we will call the model, and we're going to keep a separation between our visual representation and our model, because our model is going to be reusable in many different visual representations. We might use JSXGraph to visually represent it. We could use the HTML5 canvas. We could even use a 3D rendering and just render in some kind of plane. So we always keep it separate. So let's create a rigid body. So I'm going to create a file, and I'm actually just going to call it rigidbody.ts. Okay. Create that file, and I'm going to export a class. I'll call it rigid body, and this class is going to sort of stand in for any kind of sort of rigid body that you might care to invent. So for example, you might have something that looks like a disc, or something that looks like a square, or something, you know, whatever. The important thing is that our rigid body has properties. So we want it to have a property which is a geometric, and in fact two properties right now. One to represent the position and one to represent the attitude. Now we know that we can use the geometric to represent both of these, because the geometric number can be both a vector, which is what we need for a position, and it can be a rotor, because that's what we would need for the attitude. So by convention, what we do is we're going to name the position big X, and that's going to have type geometric. And you can see already it's saying I don't know what geometric is, so we need to import geometric. Oops. So we're going to import something from, and then the file we're going to import it from is ./e2ga, okay? Because that's the file that we have in our project. We dropped the extension, but you need to have the ./. Put that in there, Control Spacebar, geometric. So now we know what geometric is. And X is, well, let's initialize our X to, say, the origin, okay? So I'm going to go to geometric, and I see geometric 0 is actually there. So Actually, that would do as the origin. So let's go back to our rigid body. This is going to be geometric dot 0. So there we go, and we're good. So our rigid body now has a position, and let's kind of like just make sure that we can create it. So we're going to come in here, const body equals new rigid body. Okay, like that. And of course, it doesn't know what rigid body is, so we need to import rigid body. So notice that the STEMCstudio, unlike other tools, it's very natural to create new files when you kind of like create new abstractions in your program. And this is a good thing because it kind of keeps your code kind of from becoming a real spaghetti mess. So, all right, so we've now got our body. It's declared but never read. And let's, I see we've got a print line method here. Print line just writes to the document output. So let's just kind of like do a bit of sanity checking here, and we'll print line, and we'll just take a look at the body.x property, and that's equal to $ curly braces body.x. Oops, 1x will do. And the reason why it defaulted it in is because there's only one. So if I go on body.x, it's in there already. There's nothing else it could be. Okay, so our body has the position property. Now what we want to do is we want to create a visual representation of our body. And as I said before, I'm kind of celebrating Flatland here. So my intention is to kind of like create a square, maybe just out of 4 points. I'll do the 4 points, and I'll color those points in such a way that we'll be able to tell how much the body has been rotated. So this is not a realistic looking body. It's just something that we can use to gauge our progress. Now I'm going to put this in its own file. What shall I call it? A square .ts. Okay, I'm going to break from Edwin Abbott. I'm not going to call it a square. I'm just going to call it square.ts. Okay, so a square is going to be the visual representation of my rigid body. Okay, so let's create that. And it's an object, so I'm going to export a square, export a class, which is a square. Awesome. Okay, now here's where it gets interesting. What we want to do is we want this square to have 4 points. Now let's go back to index.ts and let's see how we created a point. To create a point, we need the board object. Okay, and if we hover over that, that's got type jxg.board. So we're going to need the board object. Okay, and once we've got that, then we can create the points. So what I think I'm going to do is in the constructor, I'm going to create my points. So let's go to square. So classes in JavaScript can have these special methods called constructors. And these are the first thing that gets called as part of the new instantiation. So we allocate the memory and then we use this to initialize it. So here's my board.create, and board is not known. So I'm going to pass in board as a parameter. And we know that's got the type jxg.board. All right, and so the errors go away here. Okay, and we haven't created him yet in this other file. So now I want to kind of create const s. Should I give him a name? ASQ. Oops, ASQ. I'm just going to call it square with lowercase. Failure of imagination. Okay, there we go. So a square, and you can see here a couple of problems. One is square isn't used, and the other problem here is that oh, it doesn't know what square is. So now let's import square from square. Okay. And so now it does know what square is, but it's expecting one argument, and that argument it wants is the body. Okay, so let's do that. Not the body, the board, which is why we got the arrow down there. And now everything's good. And in fact, this point here is sort of redundant because now the point is being created by the square. For the time being, let's not use the return value. Let's just do new square. And let's get a square looking something how we want it. So I want to create a unit square. Just be easier to kind of like look at magnitudes. If I perhaps make the unit 1 now, should I position this square at the origin? I think I should actually be kind of symmetrical. So like I said, I'm going to create 4 points, and I think I'll create them in sort of anti-clockwise order. So the first one's at half half, the next one's at minus a half half, next one down is going to be minus half minus a half. Okay, and then the next one is going to be plus a half minus a half. Okay. All right, so we've got something that sort of is going to resemble our square. Not going to be able to tell if this thing is rotated. Well, we got the labels actually, A, B, C, D. So we could do that, but you know what? It's going to be more fun to color it. So let's put some color on our points. So I'm going to make this color, and we want to say use a hexadecimal. And I think I'm going to make this one as an aid memoir. I'm going to make it blue. 2, 3, 4. FF, right? Bright blue. Okay, so that should remind me that like blue, it's like the correct way up is the sky. And then D, I guess I could make that like green. That would remind me that this one is sort of in the standard configuration. So red, green, blue. Red is 0, green 2Fs, blue. So in the standard configuration, we should imagine that blue is up, green is down, and they're actually on the right. Okay, and then just for fun, let's make this one. Let's make it yellow, like the sun. Okay, let's see. Didn't do wrong there. Put a pound sign in front of it. There's yellow, and the other one's already red. But you know what? I'm going to be explicit. It'll be red anyway. But it's just nice sometimes to not just accept the defaults, just in case they change. So this is going to be our square, and what we want to do is we want to be able to move our square around, and in particular we want it to move around when our body moves. So what I would like to do is I would like to bring in I would like to build the square on top of the rigid body. So I'm going to add in, say here, body as type rigid body. And by passing it in the constructor, I'll be able to have access to this rigid body at any time going forward. All right, so I need to import the rigid body from the file, which is /rigid body. Oops. Body. Okay, and the only thing it's complaining about right now is that it's never read. Okay, so what are we going to do about that? Well, for the time being, let's just kind of like have it let's make it sort of just not complain by going body dot x. We'll just use the position property. All right, now what we would like to do is we would like to make it so that when we move, oh sorry, let's fix the compile error. That's pretty easy to fix. We just need to pass in the body in here. Okay. All right, so what we want to do is we want to make it so that, I'll go to that definition, when we move the rigid body, we want this to update. Okay. Now, one way of doing that would be, yeah, well, let's kind of like just kind of like do it. So I'm going to do it in a sort of it's going to look a little bit sort of coordinate dependent here, but you have to remember that when you start kind of like crossing over the boundary between our geometric object and tools which are used to render it. Okay, give me a second here. I'll just get things straight. There we go. All right. You have to remember that when we make this transition between working in a coordinate-free way with the geometric number, which we will do in kind of programming the physics and so forth, we're going to have to kind of like get down to coordinates in two cases. One is where we actually render to a diagram like this because it actually is built out of coordinates, and the other place is internally inside E2GA, but we don't get to see that anymore. That's all hidden inside E2GA. Okay. All right. So so here you can see I'm sort of developing this so that wherever the body is, we're going to render the points relative to that. So that takes care at least of point A. Okay, now let's just see if we can see this moving. So what I'm going to do is I'm going to set the body's position to be centered here at A, and what that should do is just move everything so the unit square is over here. Okay, so I'm going to set body dot x. It always gets me. There's only one property here right now, so body dot x equals, and I want this to be, I want to sort of do it in a sort of coordinate free way. So I want it to be like 0.5 e1 plus 0.5 e2, right? Where e1 and e2 are my basis vectors in this diagram, but those basis vectors aren't here yet, and so what I need to do is I need to import geometric from E2GA / E2GA, and what I could do is I could create const e1 equals geometric dot e1, and I could call that whatever I want. Doesn't really matter. So that's taking care of the e1. We call it right, for example, the right unit, and this one might be the up unit, but we'll just leave it as e2. I think you'll get used to that pretty quickly. Okay, so looking fairly good so far from the point of view. I just did a format document to get rid of those linting errors. In that A has moved over, but everything else has to, right? So let's just kind of complete this. I'll just copy body.x. We've already got a minus there. We need to do that plus that. We can go that, and then we can paste that, and then we can drop that plus that, and then we can paste that, and presto. So basically our body is located at 1/2 e1 plus 1/2 e2, and you can see it's moved to the right. No rotation happening. Blue still up, that's like blue sky. Green for the ground, those are on the right. Sun's still up there, and little red, I don't know what that is, flower maybe. All right, so we have got position working for our rigid body, let us now introduce the attitude of our rigid body. Okay, so recall from the rotations video that we can use a rotor to represent the angle of this object, this physical object. So you might think, oh, why don't we just use, a real just angle? Why do we use this sort of slightly indirect representation? Well, a rotor is kind of like an angle on steroids, if you like. It contains both the angle information, which is just like, the radian measure, like how many radians or how many degrees are you rotating through. It contains that information, but what it also contains is it contains the sense of rotation, that's by the orientation, and it contains the plane of the rotation. Now, obviously, in 2 dimensions here, the plane of the rotation is not very interesting because there is only one plane. But everything that we do here is going to generalize, and it'll be exactly the same in 3D. But the amazing part will be that because we'll use a 3D geometric number, it will automatically be able to handle rotations in different planes, and the attitude, you just need one attitude to set the configuration of the object. Okay, so by convention, the attitude is normally given a symbol R. Okay, so let's do that. And what do you think would be a good value to set the attitude to? Well, a rotor which doesn't rotate at all is just the number 1, right? Because if you put a 1, like the way the rotor works is you put the rotor on the left-hand side of the thing that you want to rotate, like a vector. You put the reverse of the rotor on the right-hand side and you multiply it all out. Well, if R is just 1, the scalar 1, then that just doesn't do anything, right? So our default value we're going to use is 1. Not sure if I've got a constant for that, do I? No, apparently I do. Great. And you know what we should do here is we should the attitude. That'll do. And then this is going to be the position. Okay. Now you might be used to other tools where they use the words like pause and stuff like that, but well, this is the kind of grown-up way of doing it. We're going to use big X as the position, and we're going to use big R as the attitude. All right, so we have now in our rigid body an R. So the question is, how can we use R to actually rotate the points in our rigid body? So let's go with the points in our square. Okay, well, the way to do that is we can use the rotation formula. And what we need to do is we need to rotate the square first and then apply a translation. Okay, so it's becoming kind of more apparent that what we need to do here is we need to start using our geometric number more, because we don't want to get into a situation here where we're doing kind of like, crazy coordinate kind of like gymnastics, right? What we want to do is we want to really do this kind of like geometrically. So instead of having these points here just defined as numbers, what I'm going to do is I'm going to create some constants, if you like, for those, and then we can manipulate those constants. So let's do this, const, and I'll use the word A, because that's going to be this point over here. So const A equals, and again, let's be geometric. So I'm going to import geometric from /geometric. Now you might be a little concerned, oops, that's from, there's an awful lot of importing going along, and can we get into problems if you have circularities? Well, certainly circularities in general, you want to avoid them. What's the problem here? Okay, it's not being used. Let's just, and this is going to be, oh, and let's kind of like also reproduce the constants here. So const e1 equals geometric dot e1. I suppose I could have copied it from the other file. It's just kind of convenient to have little local constants here rather than be always dealing with this prefix of geometric. So a is going to be 0.5 times e1 and plus 0.5 times e2, right? So there's a. Now, but what's the actual position of a once it has been acted on by our rigid body? Okay, so what we want to do here is we need to think of a new variable. A moved. Not very original, David, but we'll work on it. A moved equals, and we want to take the body's rotor, body.r, we want to multiply it by the point A, which actually now I can see that we should have called that like a lowercase to indicate like the vector, because by convention that's kind of what you do. Sorry, talking too much. Body times A times, and then we want the reverse of this, right? And there is a reverse method, I believe. Yep. Here's A moved. And then what we need to do is we need to add to this the body's position. And with any luck, A moved is now in the right place. So I'm going to put in A moved dot X here and A moved dot Y. Okay. What's the problem here? Oh, sorry, cannot find that module because it's called E2GA, that's why. And the good news is stuff is kind of coming back. Okay. All right. It's so tempting for me right now just to kind of like go and test this a little bit. So I think I kind of will. What I want to do is let's kind of like just hide the points, these three points to start with, and just focus on the point A. What I want to do is do a little test, and I want to see if I can do a 45 or a 90 degree, let's say a 90 degree rotation. So a 90 degree rotation, put that there. A 90 degree rotation, we can make that happen if we have unit vectors that can do that. So body.r equals, all right, so what I want to do is I want to construct I need a theta here. Const theta equals, say, 45. Okay, we're working degrees. Times math dot pi divided by 180. Okay, so I've got theta. I've converted it into radians there by multiplying by pi and then dividing by 180 degrees. So body.r is math.cos theta plus math.cos theta times E1 plus math.sine of theta times E2. Okay, this is going to be our M vector. Okay, and what we want to do then is and obviously R is, this is a vector, right? But we want to have a rotor, and the way you get a rotor is you multiply two vectors together, or one way of doing it is to multiply two vectors together. So we're going to multiply it by E1 is the unit vector. And that looks good. Okay, so let me just explain what happened there. So A started over here. For it to end up over here, this square must have been rotated 90 degrees, right? If you imagine the diagonals through there, the diagonals intersect at 90 degrees. So if it rotates at 90 degrees, then A ends up here. What I did here is I set up an angle theta of 45 degrees, convert it into radians, and then I created a rotor which is the cosine of theta in E1. Oh, sorry, the rotor is the product of two vectors, and the first vector is a vector at 45 degrees, right? And I've used cosine and sine to ensure that the length of this vector is 1. The length of this vector is 1, okay? So cos theta times E1 plus sine theta times E2. Then what I do is I multiply that by the vector E1, which is the vector that goes, if it starts at the origin, then it ends up at point 1 here. So when you multiply those two things, you're going to get a rotation which is twice the angle between them. And if the angle between them is 45 degrees, then we're going to get a 90-degree rotation of A. Looks good so far. Let's kind of like bring back our other points. And actually, I'm going to bring back one at a time. B is in the same place. Let's just bring back the one that is opposite. Now called B. Don't worry about it. It's called B because it's the second one to be created, but it's not really B. You know, I mean, it's red. Okay, so yeah, we want to basically do the same, play the same game here. So it seems to me it would be good to have like a transform function here that would transform a raw vector to the position it should be in. What we're actually doing here, and I think we'll find a better name for this function. I mean, it's going to be some kind of transform, but we're essentially transforming the vector, which is the standard configuration position of like A, which is half E1 plus half E2. We're transforming it from its standard configuration, which is like the position it's in when big X is 0 and big R is 1. And we're transforming it to the place it should be when we've applied our motion. So here's our point coming in, or a vector if you like, geometric. Don't really want to call it point actually. It is, I mean, it is in a way, it's a position vector. So let's call it position. Okay. And what we want to do is we want to have this a moved kind of thing being returned. So instead of doing that, I need to return. And now we need to have the bodies R. So to transform, I need to have the body. And well, I can either have the body or I could have the body's X. Don't really know if there's a good way to discern which one is better. Okay, and instead of A, we're going to have position. And yeah, let's use this. So A moved is now transform A, and we need to pass in the body. Okay, and that should replace all of that stuff. I think we're good. Okay, this is just telling me we should end with a new line. That's, you know, just it's a sort of standard practice in software development, but we'll just conform with it and go with it. All right, now what should we do here? I think what I'm going to do is I'm going to do that. I'm just trying to simplify my variables here a little bit. So I don't need A anymore, right? And now I can just rename this and say this is point A, really. So transform actually what it does is it's going to return a vector, right? Because this is a vector. and we're just rotating it at first, and then we are adding this offset, this translation. So it kind of makes sense to think of it as kind of like returning some kind of a position vector. Well, enough of that right now. So let's kind of like just keep on going. So now let's say do this one, and this is actually point C, right? Really, when we get the labeling right, it's point C. And the location of it is going to be -1/2 in the X and -1/2 in the Y, right? Yeah, let's see. So I'm going to create this point at C dot X and C dot Y. Yay, okay, so that looks good. B is moved from, this is its standard position, over to here. And now all we need to do is kind of like go through and complete this. So let's do B. This point B. Okay, and the position of B originally is -1/2 +1/2. So -1/2 E1 plus 1/2 E2. Okay, and now we're going to create B at the position B dot X and B dot Y. And yellow is down here, yeah. So blue is moved across to here, the yellow is moved down to here, the red is moved across, and all we need to do now is to do D, which is here. Okay, and D was +1/2 -1/2. So this needs to be +1/2 -1/2. That's D. Board.create D.X and D.Y. Okay, looks good. Let us, let's see. It would be nice to make this a little bit more dynamic right now, so that, you know, we could actually kind of like see this thing move a bit. And in addition, we're going to have to kind of like do something to square to make it a little bit more dynamic, because everything's happening in the constructor here, right? So if we construct it and then we change the rigid body, as of right now, nothing happens. Okay. So we need to figure out how to fix that. Okay, so let us let's first kind of make this, well, we don't need to do anything too fancy to make this dynamic. All we really need to do, kind of like prove that we get this dynamic, is to kind of like just move the square again after, say, after we've created the body initially. And then what we'll do is we'll print out the new body X. But this time what we're going to do is we're gonna move this to, say, let's say move it to 2E2 and 2. Okay, so as you can see, body X, the position we've changed, but we changed it after we created the square, and that's the reason why the square is not moved. So how are we going to fix this? Well, there are a number of different ways that we can do it, but what I think that we should do here, a sort of standard approach, is essentially to tell the square that it needs to update itself. So we're going to kind of like create a method, say, on the square called update, saying update yourself, and then we'll implement that method and make sure the square responds. Okay, so here's our square. Let's go to that definition. Let's add a method called update. Okay, and update's not going to return anything. If you hover over this, by the way, you'll see it already says, you know, my type is void. I'm not going to return anything, but we can sort of cement that, make it so that that really is what's happening. Yeah, trailing white space. And here what we need to do is we need to move the points to follow the rigid body. Okay, so that's kind of the idea. Let's go back to here and just put the update in. So here's the body.x. We changed body.x. We're just printing it out. And now we need to have square.update. Well, we don't have a square variable, so const square. This could be square 1, square 2, Bob, Alice, whatever you want to call it. Let's go with Bob, just for fun. So here's Bob, and then Bob needs to update himself. And what we hope, a little formatting there. You can format, by the way, by right-clicking and format document. And you can also do, if you follow the keyboard, format document, Control-Shift-I. So Control-Shift-I would also do it. All right, now we need to make sure something happens in Bob.update. So let's go to that. And essentially what we're going to have to do here is sort of use the body to move the points that were created. So this is actually creating points. So what I'm going to do is I'm going to create local variables here. So what is the type of the point? It's a JXG point. As you can see there, the return value is JXG point. So I'm going to create point A as type JXG dot point. There it is, point right down there. A lot of points. Okay, and I'm gonna, that's my variable that I'm gonna use to hold point A. Okay, so what's gone wrong here? It has no initializer and it's not definitely assigned. Oh, sorry. This dot point A equals. All right, we're good. So we've remembered point A. Now in JSX graph, there is a way to move a point, and it might be set position. Yeah, I think it's set position. You have to be careful. It's not, it translates the object by that. I think it's a translation relative to its creation. It's not an additional translation. And we've also got this other argument that needs to kind of like be put in there. JXG.coords by, I'm not sure which one it should be. Coords by user and coords by screen. Okay. Let's see what the other arguments are. Chords is an array, so presumably it's just kind of like this. And let's 0, 0. That's in the way. Let's put it at 2, 2. I believe that's what we want. We can check that that's not just translating this thing away by calling Bob update again. Yeah, it's fine. It doesn't change. So yeah, that is the right method to use. So I'll leave the second update in there just for a second. Okay, let's go back to our square. Okay, so what we want to do right now is we want to, we really want to, what we could do is we could take this out, take these initial values out, transform by the body. So we need to do this dot body now, and this now can become a private member variable of the class. And we'll just now create the points all at the origin. Okay. Now you'd think, oh, that would be bad because you created it at the origin, like it's all going to be, in the wrong place. But I can go at the end of my constructor, I can go this.update. Okay, and that makes everything good again. All right, so const A, and then we need to move point A to A dot X and A dot Y. At this point, I've decided to skip forward to the final product, if you will, of the square, because there's not really that much more to see. But I will walk through some of the changes I've made just so that you can see what sort of has been going on. Okay, let's take a look at that. So as you can see, we've moved all of the set position code to the update method. And what we're doing in the update method is we're taking the original position of a point, like this is A, B, C, D, and we're transforming it using the body, which is basically performing the rotation and then adding the translation. And then you can see that we're just applying that to the point. So what that means is that for the construction, it's not necessary to actually position the point at all. We can just create the point and then we immediately update, and the points assume the right positions. One other thing I've done in this class is I've added modifiers to each of the points, making them both private and immutable. Yeah, so making it private means that when we are in this part of the code, if I type Bob dot, I only get the update method. I don't get the, in fact, I'll just show you the consequence of not doing it. We leave it like that. It works fine, sure. But here, if I go Bob dot, and you see we got point A. And I don't want to expose these sort of inner details of the square. So that's the reason why we make this private read-only. Okay. In addition, I've made the body property read-only. Making that read-only essentially just prevents us from doing something like this. Or at least it kind of creates a warning. So there you go. Oops, sorry, I need to do this stuff, buddy. There we go. Still an error, of course. Cannot assign to body because it is a read-only property. And if you did that, it would just sort of reset the square. Not something we really want to do. So that's about it. Let's see. Make sure that we're working here. That's just white space. Okay. So in summary, what have we done? We have created, I'll just hide the documentation. We have created an object, which we'll call a rigid body. Very simple right now. It's just really a collection of properties, one of which is the position, and the other is the attitude. And the attitude is a rotor, and the position is a vector. And we use that to update the position of a square, which for us is a collection of 4 points which are colored so we can see kind of what's going on. And then here in the main line, you can see the code that actually does things like perform rotations and so forth. So if I get rid of the modifications, what we should get is the body in its initial configuration. So there you go. And we don't really need to be printing that out. Okay, so in the initial configuration, we see the body looks like this, and its position is, its center is, it's at the origin, and its attitude is 1, excuse me, which means it hasn't been rotated. And if we want, we can apply a rotation. So we can apply a rotation here of, anything, 5 degrees, 15 degrees, a little bit more, okay? And we can also apply a translation, so we can move the body somewhere else. So here I might take it to 1E2 and also 1E1 and 2E2, okay? So we have everything in place to be able to use our body to simulate real physical bodies. And the way that we're going to do this is we're going to connect the position to the velocity, so that the velocity essentially is going to move the body around. And we're going to connect the attitude to the angular velocity. So the angular velocity is also going to change the attitude of the body through the rotor. I hope you found this interesting and useful. This is kind of what you sort of do. It takes a little bit of time to get a good setup of this sort of visualization of geometric algebra. But once you've got this in place, this kind of apparatus in place, then you can use it for sort of many things. So if you liked the video, please hit the like button. It lets me know that I'm doing the right things. And if you want to see more videos like this, hit the subscribe button and more will come your way. Okay, until next time, take care and happy coding. Bye-bye.